We are looking at section 9.2 and 9.3, where we're going to be talking about estimating a population mean. So we have several objectives here. We are going to learn how to obtain a point estimate for the population mean. We're going to learn about something new called a t-distribution. And then we're going to learn how to construct and interpret confidence intervals for a mean and find a sample size with a given margin of error. So a point estimate is the value of a statistic, remember statistics come from samples, that estimates the value of a parameter. Remember, a parameter comes from a population. So in our last lesson, we looked at the statistic and the parameter for the population and sample proportions. And that's what proportion of the population has a certain characteristic, what proportion has brown hair, what proportion agrees with this, what proportion has graduated from high school, some characteristic. Now, in this lesson, we're going to be looking at sample means, which remember from earlier this year, our symbol for that is X bar. And that is the symbol we use for the sample mean. So that is the mean of all of the data collected in our sample. And we're going to be using that to estimate the population mean. And the symbol we use for that is the mu, the one that looks kind of like a U with a long tail on the wrong side. There, that Greek letter, that's actually an M, which is mu. And we are going to be estimating the population mean using our sample mean as an estimate. So the sample mean X bar is the point estimate of the population mean, mu. So we're going to look at this example a few times throughout the lesson. So pennies minted after 1982 have a certain composition, and so here's the weight of 17 randomly selected pennies that were minted after 1982. We're going to treat this as a simple random sample, and we're going to use it to estimate the population mean weight. So from this data, we can find the mean of the sample, because this is the sample. So we can find the mean of all of these data points, and that would be our X bar. That is also then our point estimate for the population of, or the mean of the population, which is our mu. So add them all up, divide by 17, because we're told there's 17 of them, and we find the sample mean is 2.464. That means we would estimate that mu, the population mean, is 2.464 as well. Okay, so our sample mean is our estimate of our population mean if our sampling was done well. And in this one it says to treat it as a simple random sample. So what we're going to do now is learn about a different kind of distribution, which is called a t-distribution. A t-distribution is very much like a normal distribution, which we've studied before. And remember, in that normal distribution, the letter we used was z. Z was the letter that told us how many standard deviations an observation is away from the mean. So if z is 1, 1 standard deviation above the mean. If z was negative 2.3, 2.3 standard deviations below the mean. In a t-distribution, we can use our sample measurements. So we can use our X bar and our S, our standard deviation of our sample, to do our calculations. Whereas in a z calculation or normal distribution, we would need to know what sigma is, the standard deviation of the population, and usually that information is not available to us. So the t-distribution allows us to use our sample information. So when I took statistics in college, I could press the right buttons on the calculator and I could get the right answer, but I really had no clue what the difference was between a t and a z and why I was using one instead of the other one. Really what it boils down to is that t is a more realistic, more useful measurement, because in almost every situation, you are not going to know sigma for the population standard deviation. It's just we won't have that information. So what the t allows us to do then is use the s, or the standard deviation of our sample, instead. Now the two distributions are going to look a lot the same. So I just kind of want to get to, let's see. Okay, and then we'll go back to what those were. So here, that blue one is the normal distribution. So that is our z curve, the normal distribution curve. Those other two, the red and the pink, or the kind of orangish and the pink, those are both different t distributions. T actually changes depending on the size of the sample. Because the bigger the sample, the more sure we can be that we are adequately measuring a good estimate of the population. So as the sample gets larger, the curve becomes closer and closer to the normal distribution. So you can see the curves are very, very similar in their shape and their behavior. And so now we're going to go back and talk about what some of those behaviors are. Let's see, here we go. Okay, so some properties of the t distribution. The t distribution is different for different degrees of freedom. And degrees of freedom is just kind of a fancy terminology that says sample size. It's not exactly equal to the sample size. It's actually sample size minus 1. So if our sample size is 15, we have 14 degrees of freedom. But so as the sample size changes, or the degrees of freedom change, the t distribution changes slightly. And we just saw the picture of that. The t distribution is centered at 0, and it's symmetric about 0. That's the same as a normal distribution. A normal distribution is also centered at 0 and symmetric about 0. The area under the curve is 1, because we're thinking about probabilities. We turn these into probabilities, and probability totals must be 1. So this is also the same as the normal distribution curve. And then because of the symmetry, the left and the right hand sides are both then equal to 1/2. As t increases or decreases without bound, the graph approaches but never equals 0. A fancy way of saying that it has that asymptote as it goes out into the tails. That's the same as a normal distribution. So really, what we see here from these points so far is that t is very much like a normal distribution, except for that point number 1. That point number 1 where it says the sample size matters. Sample size doesn't matter for a normal distribution. So number 5 here, the area in the tails of the t distribution is a little greater than in the tails of the standard normal distribution, because we're using s instead of sigma. Okay, so that is a primary difference between the t and the normal, is that the tails hold a little bit more of the area. As the sample size n increases, the density curve of t gets closer to the standard normal curve. And that is what we just saw in this picture, that when t gets larger and larger and larger, the t curve is going to end up becoming more and more like the normal curve. All right, so the t-curve, we can use the same way that we use the z-curve, and we're looking at finding the area under one part of this curve. We're going to use StatCrunch to help us find the area under the curve, just as we did with our normal curve as well. With the normal curves, we looked at those tables, those z-tables. You may remember where it said like 1.2 over here, and then up at the top we would find 5, and we go oop, 1.25, and we'd find our z value there in, or find our probability value there, area value in the table from those z's. You could do the same thing with a t. The t chart is a little bit more complicated because it also then has to have the n, or the degrees of freedom, in there as well, because that changes all of that. So we're not going to use the charts here. We're just going to go straight to StatCrunch and use that to calculate our areas. So we're going to use it to calculate confidence intervals. So we talked about confidence intervals in the last section. So the idea of a confidence interval is that we can take a measurement on a sample, and that is perfect for the sample. And if we've sampled well, it should be pretty good for the population, but not perfect. And so we want to give ourselves some space and say, this is where the sample is, but I'm going to move and give myself a little bit of wiggle room on left and right and say I'm pretty sure that that will cover what the actual population measurement is. We did that for proportions in the last section. We're going to do it for our means in this section. It is exactly the same concept. Exactly the same concept. When we find a confidence interval for mu, as we found the confidence interval for p, or for the proportion in the last section. Okay. One thing about that, we do need our data to come from a population that is normally distributed, or we need the sample size to be very large. Okay, so the reason is because that t-curve is different than the normal distribution curve, we need to know that the population is normal, or that our sample size is so large that the t-curve is going to closely match the normal distribution curve anyway. So we need a normally distributed population, or at least a very big sample. Okay, so this is that process of how we take our statistic, which in this case is our x bar, and then we add and we subtract, or I don't know which way the video is going, add and subtract, whichever way makes sense. Everything gets flipped around on the camera. So we start with that x bar, and we add and we subtract some amount, which is our margin of error. The way we calculate that margin of error is by using those t values. So it says t in this one. In the last lesson, it said z. So we use those t values and then times the sigma divided by the square root of n, the standard deviation divided by the square root of our sample size. So we're going to go back to that penny problem, and we're going to find a confidence interval. So we're going to construct a 99% confidence interval for the population mean, and we're going to assume it says mu of 0.02, but it doesn't mean actually mu, because that wouldn't make any sense. It means standard deviation. So to construct this confidence interval, this is the process to go through the formula. We start with the mean, which we calculated earlier in the lesson. The mean of the sample was the 2.464. And then we're going to add and subtract from that some amount here. And that amount is the standard deviation, which is actually what they meant with that 0.02. There's a typo before. It's not supposed to be the mu. It's supposed to be the standard deviation. We're estimating mu. So the standard deviation, the 0.02 divided by the square root of the sample, there were 17 in the sample, and that gives us our confidence interval here. Now that's if we were doing it by hand, and then we would have to look up that 2.921 value off of a t-chart. So instead, let's go ahead and take a look at this in StatCrunch. So I went ahead before the lesson and entered all that data in here. So these are those 17 points of the pennies, the 17 data points. So we're going to go into stat here. We're going to choose t stats because we're using this new t distribution. So in our t stats here, we're going to choose one sample because we only took one sample of pennies. We're not making comparisons between different groups, just one sample. And in this problem, what we have is data. We actually have the weights of the 17 pennies. In some problems, you might have the actual data of what each individual value is. In other problems, you might just have a summary. It might just say, a sample was taken of 17 pennies and X bar is 2.462 or whatever it was, and S is 0.02. It might just give you those two pieces of information instead of giving you the list of all the individual data. So this one we have data. Sometimes you might just have a summary if it just tells you what those statistics are. We're going to go data. We're going to tell it where the data is, and then what we're making is a confidence interval. And this problem asks us for a 99 confidence interval. So we're going to change that to a 99, and I'm going to compute. And so right here it has our sample mean, which is that 2.464, I guess it was. And then our lower limit and upper limit, that is our confidence interval. So we are 99% confident that the mean weight of pennies that are minted after 1982 is between 2.45 and 2.48. Okay, that's how we would read that off. We give our confidence level, and then we give the lower and the upper limits, and what those are measuring is the mean. Okay, so we're 99% confident that the mean weight of those pennies is between those two values. Okay, so, and I'll just show you what it would look like if you went to the other screen. If you went and chose T-stats, so again, we're doing T's here, one sample. If we went to summary, you would have to type in our sample mean, which was, 2.464, the sample standard deviation, which they said to assume was 0.02, and the sample size, which we had 17. We're going to choose our confidence level, 99. And so we would just type in each of those given data or given statistics instead of data values, and then it gives us the same piece of information here. Okay. All right, back to our notes. All right, so now what about if we have already pre-decided I want to give myself this much wiggle room? How many people or how many pennies do I need to go weigh? How many people do I need to survey? How many pennies do I need to weigh? How big does my sample need to be if I want to give myself this much wiggle room? Okay, so we're trying to determine our sample size. Nice formula here, kind of messy. So back to our pennies. How large of a sample would be required? So earlier problem, sample is 17 pennies. That's not difficult, right? 17, we can weigh 17 pennies. That's not that big of a deal. How large of a sample would we need if we wanted to estimate the weight within 0.005 grams with 99% confidence? And then again, it gives us there, we're assuming that the S is 0.02. Okay, so into StatCrunch. We are going to go into stats, into those T-stats, one sample, and we want to find our sample size with width because it said within this much, and I'm going to need to flip back because I don't remember how much it said, but we have our width is what we know about it. So we do know we wanted to be 99% confident, and the standard deviation was 0.02. And then this width is what I forgot. So back to here, within 0.005. Now, that's 0.005 bigger and smaller. 0.005 both ways. So the width of the interval is 0.005 and another 0.005, so times 2, 0.01. Okay, our width of our interval is twice of that margin of error. So this is our margin of error each way. Got to double that to find the width. So 0.01 is the width we're going to use. A lot of students get wrong answers on the homework and then ask me why they're getting them wrong, and a lot of times that's what's happening. And when we compute, it gives us our sample size. All right, we got to weigh 110 pennies. It's still not terrible. It's doable, right? It just takes a little time, but not terrible. It's not like thousands. So we would be able to accomplish that goal then feasibly. All right. Back here. All right, they show us how to do it by hand. And that's the end of 9.2. Now 9.3, it's like only one slide because it's, okay, so now we've learned confidence intervals for two different things. So which one do I do? Because when you're in your 9.1 homework, you know you're going to go to those proportion stats. When you're in your 9.2 homework, you know you're going to go to those T-stats. When you're in your quiz, how do you know which one to go to? So what are we estimating? Are we estimating or measuring a proportion? Okay, then we got to go to those proportion stats. Are we estimating a mean? Then we need to go to those T-stats. Now, with the mean, it gives us some more information here. So remember in the last, or earlier in the notes in this video, but last lesson, I said that the population either needs to be normally distributed or a large sample, but large is relative, right? Here, this gives us a better specification of what do we mean by large, bigger than 30. Okay, so If we are estimating a mean, we need our sample to be bigger than 30. Go ahead and do a t-interval. If the sample is not bigger than 30, then we have to ask ourselves if the data comes from a population that is approximately normal with no outliers. If so, we can go ahead and do that t-interval. If not, we have to use some other methods that you don't know yet that are called non-parametric or bootstrap. We haven't learned those. So you're going to have to go ahead and figure that you probably aren't going to have to do those, but it is going to ask you questions in your assignment about, can we do this even if we don't know that our population is normal, right? If we don't know our population is normal, we need a sample size of 30 or larger. By the way, sample size of 30 or larger, that sounds a lot like your project, right? So for your project, you need a sample of 30. That's why. That's why you need a sample of 30 and not just like 25. It wasn't randomly chosen. We need that sample to be 30 or larger, so that even if the population is not normally distributed, you'll be able to calculate these t-intervals later in your project. Then it also talks about here estimating our standard deviation. That's in green because that's something that we didn't actually cover in this chapter. It's just like bonus. You can also estimate standard deviations, but we're not going to be doing that in this chapter. So if the question uses the word proportion, then go to those proportion stats. If we're estimating a mean, then we're going to use or a sample that is greater than or equal to 30. All right, that's the end of chapter 9. So let me know what questions you have as you work through your assignments, and I'm happy to help with those. See you later, guys.